Good afternoon, everyone. Welcome to the day 3 of online faculty development program on AI in cloud computing, theory, practice, and application. So, in today's two sessions, we are going to discuss about some of the optimization techniques which are applied in the field of cloud computing. So, optimization techniques are one of the important subcomponents of artificial intelligence. So we have planned to cover some of the optimization techniques which are applied to various research area of cloud computing. So specifically, we are going to discuss in this session about the genetic algorithm, how genetic algorithm is applied into the field of cloud computing. And in the subsequent lecture, in the second lecture, we'll also discuss about one of the two popular algorithms. One is TLBO, that is called as teaching learning based optimization, and Jaya algorithm, which is an extension of teaching learning based optimization. And we'll see how these two algorithms can be applied into cloud computing. Then maybe in the next week we have another optimization technique that we are going to cover. That is particle sum optimization. How PSO can be applied to solve some research problem in cloud computing. So let us start this first session in which we are going to discuss about the genetic algorithm. So I'll tell you about the basics of genetic algorithm. Then we'll go for that cloud computing problem. Basically, I'll tell you about one of the very popular problem in cloud computing, that is called as task scheduling problem. So we'll see how a genetic algorithm can be applied to solve the task scheduling problem. Okay, task scheduling comes under one of the very popular problem in cloud computing. There are different ways to formulate the task scheduling problem. Many people have referred a single cloud. Many people have referred multiple cloud. They have also referred homogeneous environment, heterogeneous environment, and applied various optimization technique, not limited to genetic algorithm, to solve this problem. So these are the contents that we are going to discuss. I'll give a very brief idea about all the optimization technique, why these optimization techniques are popular. Then specifically, I'll tell you about genetic algorithm. Then we'll see what is a task scheduling problem and how to solve that particular problem using genetic algorithm. I'll tell you in very detailed level, and I'll also show you some of the representations, how to formulate a particular problem, how to map the problem with genetic algorithm. So that we'll discuss. Then you can see that how we can achieve our objective of the task scheduling. So again, nowadays also people have focused on energy efficient cloud computing, in which we focus on energy part. But if you go for traditional task scheduling algorithms, we more or less focuses on the completion time. So irrespective of objective, we have different type of a problem, right? So we'll discuss about that particular problem. Then I'll show you in between also, I'll show you some of the applications like you may aware of Huffman coding, you may aware of I can say NAPSA problem. These problems can also be solved using optimization technique. So that also we are going to discuss, followed by conclusion and references. Now we do know that when we are solving any scientific engineering problem, so these problems are complex in nature. So modeling of these problems is more important. Before solving a problem, first you need to model that particular problem. We have studied number of optimization technique, but based on the input to the optimization technique, we have to model our problem. So if you go for a large scale problem in which you want to solve it in a traditional way or conventional way, so it is very difficult, because if you go for the traditional techniques like linear programming, or you can go for dynamic programming techniques. So in which we model the problems with a number of variables. And in your problem, if you have very large number of variables, then it is difficult to solve. And objective functions that are used in such type of problem is generally linear in nature, right? So, but when you go for real life problems, you can find the objective function is non-linear in nature. So there is a difference between the linear objective function and non-linear objective function. I'll tell you in subsequent slide. But mostly the problems which we are solving using traditional technique, they are having linear objective functions. So if you solve that problem, any problem using the traditional techniques, so we can reach to a local optimum, but it is difficult to reach the global optimum. And sometimes also our problem is failed. Sometimes it is not reaching to towards the solution, or what we call convergence rate is very slow. So in order to avoid these problems with the traditional technique, we come up with various non-traditional optimization algorithms. And sometimes we refer these non-traditional optimization algorithm as meta-heuristic approaches, or we call as soft computing approaches. So if you apply a meta-heuristic like genetic algorithm, you can say on later section we are going to discuss about TLBO and Jaya algorithm and particle sum optimization. You will see we are, if you solve using a non-traditional method, then we can reach to the near to the optimum solution. For example, if the optimum solution is 2, then you can reach the value 1.99, okay, or 2.8 zeros followed by 1. So these solutions are very close to the optimum solution. Okay, that's why we are applying the non-traditional optimization algorithm. Especially non-traditional optimization algorithms are suitable when your objective function is non-linear, right? If objective function is linear, complexity is less. But if the objective function is non-linear in nature, it is really challenging. So let us understand that what is the difference between a linear objective function and a non-linear objective function. So here I am showing you two pictures. By looking into this picture, you can see in the first picture, we talk about a particular line. We all know the line equation y is equal to mx plus c. We have slope, we have intercept. So if there is a straight line, okay, so if you want to find an optimum, the optimum is always attained at a constant boundary. And if you found the local optimum solution, the local optimum solution is same as the global optimum solution. Like example, in a class of 60 students, let's say one student is secured the highest mark, right? So that student is considered as the local optimum solution, right? Because we are talking about a particular class. But that student is also secured highest mark if you consider all the branches or all the sections. Then we can say the local optimum solution is global optimum solution. So it is possible when our objective function is linear, but mostly our objective functions are not linear. So in that case, if the objective function is non-linear, so optimum is not guaranteed that it is always going to be present in the constant boundary. So it may be interior, it may be in boundary, it may be anywhere, right? So in that case, the local optimum solution is not the global optimum solution. So linear objective function means we more or less related to the line y is equal to mx plus c. But when you go for nonlinear objective function, we look into a curve, right? For example, if you look into this particular picture, which shows the nonlinear objective function. So in which suppose I want to find the maximum height. Okay, you can see this just like a hill, right? Suppose I'll ask you, you find the maximum height. Okay, and assume that you found that suppose you are now your current position is here. So you can move from your current position to the next position if the height is more. So obviously you are going to move from this point to this particular point. Again, you are going to move to this particular point. But when you reach to this point, okay, which is top of that particular hill, then if you find the next step, it is not, the height is not going to be increased. So you have to stop here. So this solution you can claim is a local optimum solution, but you cannot assure that it is a global optimum solution. But if it is happens in the case of linear objective function, then we can claim local optimum solution is same as the global optimum solutions. So as we cannot claim it, so we cannot reach to global optimum solution using the traditional methods. That's why we are going for non-traditional optimization methods. Now, if you go for non-traditional optimization methods, like we talk about genetic algorithm, particle swarm optimization, there are many optimization algorithms which is based upon our natural phenomenon. For example, you are observing the pattern of a particular animal or particular behavior of an animal or particle or whatever may be, right? So by looking into that, you are deciding, right? By looking into that particular pattern, you want to observe their behavior and you want to model it in the form of a mathematical equation. So mostly these algorithms are based upon the natural phenomenon, or we can say what we observed in our real life. Okay. So sometimes you can see that we need to update the solution. You may not find the solution in very fast iteration. We have to do a couple of iterations to reach to the final solution, right? So reaching from a initial solution to the final solution, we call that as a convergence rate. So sometimes we have faster convergence and sometimes we have slower convergence also. But if you see, these algorithms are mostly stochastic optimizations. So stochastic optimizations always takes the random numbers, right? So here randomness is present. Like if I ask you, uh, generate a random number between 1 to 100, right? So we don't know which value is going to come, right? Similarly, whatever value you are going to get now, if you rerun again, then you may not get the same value. So there is a change in that particular value also. Irrespective of the optimization technique, you will find some randomness is there. But overall, they are based upon based upon two extremes, combination of two extremes. Or if you go for working principle of any optimization technique, you will find two extremes. One is the random search, another is called as hill climbing. So random search is also referred as extreme exploration, and hill climbing is referred as extreme exploitation. So I told you two different type of search, right? One is local search or local optimum, another is global optimum. Okay. So you have to make local search as well as you have to look into all the space, that is called as global search. So random search is trying to get the global search. However, hill climbing trying to get the local search. So not only local search is important, but global search is also important in order to reach to the global optimum solution. But there is always a trade-off between these two. So if you do local search, then it may happen that you may get a local optimum solution. Okay, sometimes local optimum solution is also a global optimum solution. But at the same time, you have to also see that you are exploring all other areas in the source space. So pointing to a particular part of the source space is not the solution. You have to explore all the parts. Wherever you are achieving some good result, you have to explore that part locally. So in that way, there is always a trade-off between these two factors of local search and global search. Now, if you categorize these optimization technique, so they can be broadly divided into three parts. One is called as evolutionary algorithm, another is swarm intelligence algorithm, another is author nature inspired algorithm. Okay, so these algorithms are there from long back, but if you have a new problem, not only in the area of AI and cloud computing, any area, whichever you like or whichever you are carrying out your research work. In that case, if a problem is new, okay, and the solution is too many, and it is not possible to go for exhaustive search. Exhaustive search means all possible solutions you cannot explore. So in that case, you can apply the genetic algorithm or any swarm intelligence algorithm or other nature inspired algorithm. So under evolutionary algorithm also so many algorithms are there. So some of the algorithms you can see here. One is genetic algorithm, which we are going to discuss in this session. Similarly, we have genetic programming, evolutionary strategies, differential evolution, bacteria foraging optimization, and artificial immuno algorithm. So these are some of the examples of evolutionary algorithm. We will more focus on genetic algorithm. Similarly, under the category of swarm intelligence algorithm, we have particle swarm optimization, which we will cover in this program. And apart from PSO, we have artificial bee colony optimization, ant colony optimization, shuffled frog leaping algorithm, firefly algorithm, glowworm swarm optimization, and many other algorithms comes under the swarm intelligence algorithm. Similarly, we have other nature-inspired algorithm. If you see the list, you will find simulated annealing, which is based upon the temperature. And sometimes we also look into a different type of games where we are applying the genetic algorithm and simulated annealing also, if you want to solve that particular problem. Similarly, we have harmony search, we have teaching learning based optimization algorithm, which we'll see in today's second session. Similarly, charge system algorithm, central force algorithm, cross entropy, cuckoo search, grenade explosion method, biogeography based optimization, Jaya algorithm, and three variants of Rao algorithm, which is these three algorithms are published in the recently, right, in the year of 2020. So under this nature-inspired algorithm, we'll see two algorithm in as a part of this faculty development program. We are going to discuss about teaching learning based optimization and the extension of teaching learning based optimization algorithm, that is called a Jaya algorithm. So let us start the first one, that is comes under the evolutionary computing. Okay, or evolutionary algorithm, that is genetic algorithm. One of the example of that is genetic algorithm. So we'll focus on the genetic algorithm. Now, if you go to the history of evolutionary computing, you can see it was quite old, I can say. It was developed by I. Richenberg in 1960. 1960 means you can say around 64 years back, right? If I consider 2024, 64 years back. So evolutionary computing is not new, but the type of application where you are applying this evolutionary computing is that part is new. Similarly, after the development of the various evolutionary, after development of evolutionary computing, the genetic algorithm under evolutionary algorithm was developed by John Holland, who belongs to University of Michigan in the year of 1975. Again, if you see closely, it is 50 years back. But that is traditional genetic algorithm. You can see genetic algorithm itself has several variants. And nowadays also people have make hybridizations, or they are adding some of the new operators into existing algorithms, and they are showing that their solution is more better in comparison to the existing one, right? So soon after the genetic algorithm development, the fast algorithm, which fast application, which was taken in the field of structural engineering. You know, structural engineering is a part of civil engineering by two of the popular authors. They are Goldberg and Santani in 1986. So this is the first algorithm people found in the field of structural engineering, which is uses the genetic algorithm, right? And later point of time, people have applied in their respective problem. Like I can say in computer science, people have applied genetic algorithm in mobile radar network. They've applied in vehicular radar network. They've applied in wireless sensor network, cloud computing, other fields also they've applied to solve this particular problem. But in each and every optimization technique, you can see our objective is either to minimize or our objective is to maximize. For example, if I consider time is a time I consider as a objective function. So let me tell time in the form of a function. Let it be xt. where t is time. So our objective is always either to maximize this objective, or our objective is to minimize this objective. Like time case, I can say minimize is better, because the faster computation is always better uh, than the slower computation. But when we talk about profit of a particular company, then we consider that profit of a company need to be maximized. It should not be minimized. Okay, it should be maximized. So based on the different type of problem, you can find whether you have to minimize it or you have to maximize it. That is the role of objective function. Now let us consider a set A, right? Let's say set A consists of several elements. Let it be x1, x2, x3, x4, and so on. Let's say up to x4 I am taking for an example. So I am taking a set with 4 elements, right? So you have to find a particular element which is x0. Okay, so x0 may be x1, x0 may be x2, x0 may be x3, or x0 may be x4. It may be anything. It may be x1 or x2 or x3 or x4. So you have to find a element x0 in this particular set if it exists such that f of x0 is less than equal to f of x, or if it is a minimization problem for all x belongs to A. For example, let us take a numeric example. Like I am taking A is equal to 1, 2, 3, and 4. Okay. And you want to find the square of the number. So first you have taken x0 is equal to x1. Okay. Then we'll take x0 is x2, x0 is x3, x0 is x4. Okay. So I'll find, I'll put this in function, in a particular function which I want to maximize. Suppose let's say our objective is to maximize. So I'll find the particular value. So if I find 1 square, you know it, I'll get 1. 2 square, I'll get 4. 3 square, I'll get 9. 4 square, I'll get 16. Okay. So x0 I'm taking is the first value and making square. But when I check x0 with another value, that value is larger in comparison to the previous value. Similarly, when I check the third value, that value is more larger than the previous value. Similarly, when I check 16, it is highest among all other values. So I can say here, if you look into this particular part, I can say f of 4 is less than is equal to f of x, where this x may be any value, right or not? If you take x value as 1, then it is 1 square. Okay, it is obviously if you take f of x0, sorry, this is a maximization problem. Just a minute. Okay, this is a maximization problem. So I have to take the second one, not the first one. First one is for the minimization. Second one is for the maximization. So if I take this one, okay. So f of x, you take x is any value. You can take 1 or 2 or 3 or 4. You will find f of x is less than is equal to f of 4. So f of 4 is, we know, that is 16, right? If I consider it is a squared function. So any value you want to take, you take it. The value should be less than equal to 16. But when you go for minimization problem, you know the minimum value is 1. So I can write f of 1 is less than is equal to f of x. So you take any value, you will find that value is greater than equal to f of 1 value. So in any optimization algorithm, in a particular source space, you will find some solution. Like in this set A, I have 4 solutions. Out of 4 solutions, our objective is to find the either the minimization minimum value or to the maximum value, which leads to f of x is maximum or f of x is minimum. Okay, that is the overall goal of any optimization algorithm. But when you apply the genetic algorithm, so there are some important discussions related to the genetic algorithm. The first discussion says that I told you, when you are applying if you want to solve any research problem using genetic algorithm, first you need to focus how to model the input of genetic algorithm with your research problem input, right? You have to properly model, then only you can do. So this process of modeling starts with okay, the process of this the modeling is depends upon this is called as encoding. Okay, the process is called as encoding. So the first important question arises here: how variables in genetic algorithm are encoded? Right? How to encode our problem with genetic algorithm? That I'll tell you while I'll discuss with the task scheduling problem. I'll show you how to carry out the encoding process. Second question arises: how fitness function is calculated? Okay, suppose you have 5 solutions. Okay, so you need to know which solution is more fit, okay, or more better. So for that we are calculating fitness value, okay, by using some particular function. So you need to know which fitness function is a more appropriate. Sometimes we can take the mathematical measures like standard deviation as a fitness function also. Okay, then there are number of selection methods are also there in genetic algorithm. So which selection method you will apply? Because you can see there are number of selection method I have written here. I'll tell you in detail. Like ruler till selection and Boltzmann selection, tournament selection, steady state selection. These are different type of selection methods, right? So which selection method is you are going to select for your research problem? That is also quite challenging. Similarly, you have a group of solutions. Like if you take a source space, in that source space, there is not a single solution. There will be many solutions, right? So out of this pollution, how to generate the new populations? So that is called as reproductions. So we have to create a pool that we call as a mating pool, or that is having a group of population or reproductions. So that is also important, how to make reproductions and which operation or which operators you are going to apply to the population. Okay, there are a number of operators we have. So which operator is you are going to apply to the mating pool, that also we need to finalize. So some of the major questions arises in the case of genetic algorithm is that does an optimal solution exist? Suppose you are solving a particular problem using genetic algorithm. First you need to ask whether an optimal solution exists or not. Because in mathematics, if you go for sphere function, so sphere function case, we know the optimal solution is 0. So there's optimal solution exists. So if optimal solution exists, then you can ask the next question: is it unique? Because sometimes we have so many optimal solutions, okay, and optimal solution is not unique, and there are different ways to reach that particular optimal solutions. So you should know what is the procedure to obtain a unique optimal solution, or if there is more than one solution to one of the solution. Okay, that procedure we should know. Next is how sensitive the optimal solution is. Okay, or how the solution behaves if small change in parameter. So in a particular system, the system depends upon some inputs, right? So if we vary the input, whether it is affecting the output or not, okay, or how sensitively, suppose I'll change it to let's say 0.1, then I may observe that there is a no change, or I may observe that there is a drastic change. So that's why when we do this one, whether small change is going to impact or not, that we can also look into. So these are some of the questions which we'll address in subsequent slides that you can see. Now, in which case you are going to apply genetic algorithm? There is a misconception that irrespective of the type of the problem, you can apply the genetic algorithm. That is wrong. So you cannot apply genetic algorithm to a problem if this criteria, whatever I'm going to discuss, that is not satisfied. Okay, so genetic algorithms are good at taking larger, potentially huge source spaces and navigating them, looking for optimal combination of things and solutions which we might not find a lifetime. So if you are taking a source space where source space is very large, finding the solution is not possible the lifetime of a human being. If you go for all possible solution, you will not get a solution in your lifetime. In that particular case, you can apply the genetic algorithm. For example, if I consider 16 different machines we have, okay, in a lab you can consider we have 16 different machines, and if I consider there are 512 number of tasks are there, right? So you can see the first task can be assigned to first machine. It can be assigned to the second machine. Similarly, it can be assigned to the 16th machine, and so on, right? A different way we can allot, we can assign the task to the different machines. But if you go for exhaustive search, that is all possible search, you will find total number of combination is 16 to the power 512. So if you type 16 to the power 512 in your calculator, you will uh, not get the value. Sometimes it shows infinity, right? Because you can also see 16 to the power 512 is much greater than 10 to the power 512, and 10 to the power 512 we know 1 followed by 512 number of zeros. So these many solutions you have to check in order to find the optimum solution. So it is not practically feasible, because if I say one solution takes 1 second time. Okay, so imagine 16 to the power 512 solutions. If I check how much time is required. So if you look into that much time, you will find you will not get a solution in your lifetime. So in that particular case, you can apply the genetic algorithm. Not only genetic algorithm, any optimization technique, whichever we are going to cover as a part of this course, or whatever you know from other sources, you can apply such algorithm to solve your particular problem. So there are three most important aspects of using genetic algorithm. The first one is called as objective function. So I told you in the previous one, objective function, either you need to minimize, or you want to maximize. So based on different problem, you can decide whether you have to go for minimization or you have to go for maximization. Next is we have genetic representation. Genetic representation is called as encoding, right? Okay. So encoding means for a particular problem, how you are going to model the input with genetic algorithm. That is called as encoding. And third operator is there are different type of operators we have. Because when you go for reproduction, you need some kind of operator. Like if you go to mathematics, you can say addition is an operator, multiplication is an operator, subtraction, division is considered modulus. These are called as operator. Similarly, we have some genetic operators. So that these are the three important parts in the genetic algorithm. Not only that, there are several other inheritance operators are also there, or we call them a low-level operators. Like if you know about the NOT gate, you know when we give input 0, we are getting the output is 1. Or if you give value 1, you are going to get the value of 0. Okay. Or you can go for right shift, left shift, you can go for deletion, you can go for inversion, you can go for dominance, you can go for intra-chromosomal duplication, you can go for speciation, migration, segregation, translation, sharing, mating. Lot many inheritance operators are there. But we are not using all types of operator. But these operators are alternatives to us. So whenever we model, we can use some of the operators in our life cycle of the genetic algorithm to generate a new population. So here basically we focus on three different basic operators. First one is called as reproduction. Reproduction always happens with two different population. Okay. Second one is crossover, which actually enables the process of reproduction. So complete phase we can find a set of crossover followed by a set of mutations. So in order to go for the process of reproductions, you can say in the process we are using the process of crossover and process of mutation. So now you can see this cycle, or we can say flow chart, to understand the genetic algorithm in a better way. For example, you can see we have initial population. So initial population is requires, if you want to go for initial population, the first process you have to do is encoding. Okay, first you have to perform encoding, and every encoding, or we in genetic algorithm terms we call as chromosome. So every chromosome is giving you a solution. Okay, so you can have to take a group of chromosome as initial populations. How many you have to take, that is challenging. right? Sometimes we take 50, sometimes we take 100 also in the initial population. Then we are applying the selection process, selection techniques on the initial populations, right? Selection technique is going to discard some of the population, and selection technique is going to generate some new population also, right? Or it may duplicate some chromosome also population, chromosome or population also, right? So after the process of selection, we are getting the process of new population. Then in new population, uh, once you reach to the new population, as you can see the arrow mark, the process of initial population followed by selection followed by new population. So it is done only once, right? It is done only once. Then we start a loop, right? So first we check that whether the termination condition is satisfied or not. Sometimes we can say termination condition is number of iterations. So if number of iteration is 50 or 30 or 20, something we can decide. So if termination condition is satisfied, then you have to make out of this particular loop. But if the termination condition is not satisfied, then you have to go for one of the operator that is called as crossover. Okay, so crossover is always applied to the parent. Crossover is always applied to the parent. So parent means in the new population you have to select two parents. Okay, as the termination condition is not satisfied, you have to take two different population from new population and apply the process of crossover. So once you perform the process of crossover, you will get two children. By taking two parents, you are getting two children. Then you will apply the process of mutation to the children's. Then you will get the process of modified children. So mutation is always applied to the children. Mutation is not applied to the parent. Okay. So after applying mutation to the children, you are getting the modified children. So now you have two parents, two children, and two modified children. So comparison always takes place between parent and modified children. Okay. So when you compare the performance of two parents with the two modified children, you will check their fitness. So based upon fitness, you can declare two of them. So total is four. Two is parent and two is modified children. So you have to select only two out of four, right? By saying that their fitness is better. So if their fitness is better, then we declare them fit. Okay, if children are better, then we have to replace the children by parent. But if parents are better than the modified children, we will keep it as it is, right? And if they are not fit, even say if the children are not fit, we are going to discard such children. But if parents are also not fit, we are going to discard the parents and replace with the modified children. So you can do a a number of times you can perform the crossover, and number of times you can go for the process of mutation and check their fitness in order to update the new population. And this particular loop, it is going to be executed several times until unless the termination condition is satisfied. Now let us see these steps in the remaining slides. I'll tell you about initial populations. Initial population will see selection, new population, crossover, mutation, that I'll tell you in subsequent slide. Now let us start with the first one, that is source space. So I'm talking about a source space. For example, if you model a particular problem with two variables, one is x1, another variable is x2, and I'm mentioning the values of x1 and x2 is in the range of -5 to let's say +5. So my source space is -5 to +5 for variable x1 and variable x2. Any value you are picking from -5 to +5 is a solution. Okay. So in the source space, you have a set of solutions. Okay. All solutions are called as feasible solutions, right? So if they follow your representation, then we call all are feasible solutions. One solution may be a better solution, another solution may be a poor solution. But every solution is giving you a result, right? Result may be good or bad. So the space for all possible solution is called as the search space. and each solution can be marked by the fitness value. Like if you take, let's say, solution 1, solution 2, solution 3. Let's say solution 1 case, the fitness value is better. Okay. Let's say it is a minimization problem. So it is giving you 10. Solution 2 is giving 15. Solution 3 is giving 18. So in comparison to these three solutions, the first solution is better if it is a minimization problem. So each solution can be marked by its fitness value of the problem. And we are looking for a solution. Looking for solution means looking for extreme. Either you are looking for the minimization or you look for the maximization. So when this source space is large, as I mentioned earlier also, when the source space is complicated and you don't know how to reach the solution, okay, or where to start, where you will get the appropriate solution, in those cases, optimization technique is more appropriate. So specifically, genetic algorithm, as we are talking, I am saying genetic algorithm is useful in such type of problem. So let us take the example here. Suppose I am taking a unconstrained optimization problem in which our objective is to maximize a function that is f of x. Okay, and the value of x, okay, it is in between the lower bound and upper bound. Okay, there is a lower bound and there is a upper bound. Okay, suppose I can say, like I mentioned in the previous slide, -5 to +5. -5 is my lower bound and +5 is upper bound. And you can take any number of values. Somebody can take -4.23, somebody can take -3.21, somebody can take 4.21, and so on. So if we want to minimize f of x, okay, like here our objective is given as maximize f of x. But if you want to minimize f of x, where you are sure that f of x is greater than equal to 0, so you can flip that one. That means minimizing f of x is same as maximizing 1 by f of x. Minimizing f of x is same as maximizing 1 by f of x. But if f of x is equal to 0, if f of x value is equal to 0, then it will leads to 1 by 0, and 1 by 0 is not defined. So in order to avoid this one, we are adding a small quantity into the denominator, that is 1 by f of x. So this happens when f of x value is greater than equal to 0. But if f of x value is less than 0, then we can say maximizing minus of f of x. So initially, if you see, genetic algorithm was applied to the problems that are maximization in nature. But later point of time, minimization problem also solved using genetic algorithm by converting the minimization problem to the maximization problem. So let us see one of the applications. So, and in this process also, we are going to discuss about the encoding. Because after encoding only, or after the encoding representation, you are going to apply, we are going to the phase of initial population. Okay, you will prepare for some set of solutions, right? So all of us know one of the well-known problem that is called as NAPSA problem. Okay, that is called as NAPSA problem. So in the NAPSA problem, NAPSA is simply a bag. Okay, so suppose like we are taking carry bags, right? So there are in every bag is having a capacity. We should not exceed that capacity, and whatever items you are putting in your NAPSA, and that is having a value, right? So it is having a capacity. Every item, whatever you are putting in the NAPSA, it has a size and it has a value. For example, you visited a, let's say, a shopping mall, right? You visited a shopping mall. In that shopping mall, let's say for easy presentation, I can say total 12 items are there, right? So if you are taking a particular item, we represent it by 1. So if you put that particular thing in your knapsack, okay, or if you want to carry that particular item, that is called as 1. But if you don't want to carry, then I can put the value as 0. Okay, so like if you see chromosome A or population A, in that case, you can see I'm interested to purchase the first item and the third item, okay, fourth item, and sixth item, seventh, and 11th and 12th item, right? Similarly, if you go for chromosome B case, I am taking the second item, fifth item, sixth item, then I can say ninth item and 10th item. So whether it is a chromosome A or chromosome B, okay, that is providing a valid solution. So based upon your absorb capacity, you are going to select some item. Okay, again, selecting a particular item and its value is different. But if overall capacity is not exceeding, then you can take as many as number of items are possible. So chromosome A is providing a solution. Chromosome B is also providing a solution. Maybe you can say chromosome A is case, let's say the value is more. Okay, but chromosome B case value is not more, right? That type of conclusion you can make. But every chromosome or population is giving you a solution. So, for example, if you go with a 4-bit binary to represent 16 numbers, right? Suppose you have 16 possible. Like here, I am taking 0 and 1 because it is a binary number, right? But if you want to take a, let's say, a problem in which there are 16 possibilities there. Okay, so you can represent in 4-bit binary. So if there are possibilities 4, you can represent in 2-bit binary. Like that, you can make a encoding process. So for example, if I take two variables, one is x1, another is x2. Okay, x1, another is x2. Okay, x1, for example, I can say the range of x1, you can take the lower limit is 4 zeros and upper limit is 4 1. So for example, I want to select x1 is equal to 1011. Similarly, x2 is another variable in the range of again 4 zeros to 4 1. Okay, so I am representing x2 as 0 1 1 0. Right? So x1, x2, okay, together I can say 1011 and 0 0 0 1 1 0. What is their range? Their range is x1 case you can take 4 zeros, x2 case also you can take 4 zeros. X1 case you can, like, highest value is 4 1, and x2 case also you can take 4 ones. Okay, so based upon how many number of possibilities there, you can make a conclusion that whether 4-bit is sufficient or you have to go for 6-bit or 10-bit, that you have to decide. For example, not necessarily always the limit is there in the range of 0 to 15. Like 0 to 15, total number of possibilities 16. If I go for 0 to 31, the number of possibilities 32. So not necessarily always you will get a appropriate range. Sometimes the lower limit is given as 2 and upper limit is given as 17. So 2 to 17 also, if you see 0 to 15 as you calculated 16. So 2 to 17 also you can say maximum number of possibilities 16. Right? Maximum possibility you will get is 16. So on that case, 2 is going to be encoded as 4 zeros, and let's say 17 is encoded as 4 1. Let's say. So not necessarily always the equivalent decimal will be representing the equivalent decimal will represent the binary. So it may represent anything. For example, you can see, suppose I want to find the decimal value of 1010 where my lower limit is 2. So 1010 always representing a decimal number 10. But as my lower limit is 2, so I am getting 12 by using this particular formula. So it is not necessary to code all variables in equal substring length. Another example you can see here, xi also need not be equally distributed so as to apply the linear mapping rule. For example, here you can see we are using 16 different possibility starting from 4 zeros to 4 1, and the decoded value is 0 to 15 to represent the fiber angles. So 0 is representing fiber angle is 0. 40 is representing the fiber angle is 0. Similarly, 0001 is representing the fiber angle is 10. 0010 is representing the fiber angle is 20. 0011 is representing the fiber angle is 30. 0100 is representing fiber angle 45. So the difference between two different fiber angle also may not be unique. Like here you can see the difference is 10, while I'll tell you this, the difference is 15. Right? That's why xi did not be equally distributed whenever you are going for the process of encoding. And not necessary that you will go for binary encoding. These are binary encoding, right? Because everything is represented in the form of 0 and 1. So sometimes we can go for octal encoding also. We can go for hexadecimal encoding also. So if you go for octal encoding for a variable x1, so it is 4 zeros to 47, because you know the octal case we have 8 values 0 to 7. Similarly, x2 case also you can say 4 zeros to 47. Okay, so this is the encoding. But if you go for hexadecimal, x1 can be represented as 4 zeros to 4f. Okay, because our numbers hexadecimal number system we have 0 to 9 and a to f. Similarly, x2 case we have 4 zeros to 4f. Okay, so not necessary. Mostly we follow the binary encoding, but you can go for octal encoding as well as hexadecimal encoding. Similarly, if you go for permutation encoding, okay, permutation encoding, like if I take a traveling salesman problem. So we know the traveling salesman problem, a salesperson has to visit number of cities and it has to visit each city, each city exactly once, and the starting city is equal to the ending city, right? For example, I have 9 cities. So my chromosome length is 9, right? Like I am also showing you two different chromosome here, chromosome A and chromosome B. Okay, and you can see I'm starting from, let's say, city 1, and I have to again reach to city 1 by visiting all other cities exactly once. So I have to check that all the cities are covered or not. Like you can see here, 1 is there, 2 is there, city 3 is there, city 4, city 5, city 6, city 7, city 8, city 9. So all 9 cities are there in chromosome 8. So I can consider this is a valid chromosome. But when you go from chromosome B, again I'm starting from city 8. Okay, so I have to check all other cities are also there or not. Like city 1 is there, 2, 3, I can say 4, 5, 6, 7, 8 is the initial city and 9 is the last city, right? So both chromosome is valid, but you can say, let's say chromosome B path is better than the chromosome A path. That we can make a conclusion, but it is not. It is not. We cannot infer that one of the population is not correct. But if I take a chromosome, let's say C, I am taking a one chromosome, let's say chromosome C, and I am writing like this. Let's say 1, 2, 3, 4, 5, 6, 7, 7, or 7, 8, then 7. Okay. So if you see this particular chromosome, so its length is 9, but 7 is repeated twice. So it is not considered as a valid chromosome. But all valid chromosomes are providing you a solution. Okay, like these two chromosomes, one of the chromosome will provide you a good solution, but all chromosomes are providing you at least some solutions, right? So sometimes we need genetic operator corrections. Like here, I need to convert either this 7 to 9 or this 7 to 9 to make this particular chromosome as a valid chromosome. So sometimes whenever we are generating the chromosomes, so we found that there are some chromosomes which are not correct. Okay, their sequence is not correct, or there is some mistake. So what we are doing in that case, we simply correct such genetic operators. Okay, we call that call that is a genetic corrections. We correct that one, then we include in the initial population. Similarly, for different type of problems, I am telling you all the problems with respect to the integer values, and we are representing in the form of binary, but not necessary if you are solving a particular problem. Suppose you are dealing with a problem where there is a x coordinate and y coordinate. Okay, you have a x coordinate and y coordinate. Okay, so in such cases, you will go for real numbers like 1.234, 0.456, 4556, 5.3243, 2.0253. These are some real numbers that can be also used for encoding. Similarly, sometimes we can use alphabets, or sometimes we can also use some accents. Like mostly the robotics application, we use back, right, forward, left. These are the different type of I can say operations that we are applying into the chromosomes. So they can also used for the process of encoding. Like one of the example in the application, I can say if you go for the process of neural network, in neural network we have a input layer followed by a set of hidden layers followed by a set of output layer, right? So as we have a set of hidden layers, and one I can say one neuron is connected to another neuron where we have to update the weight value. So on that case also we can apply genetic algorithm to uh, represent the in if you apply genetic algorithm to solve that particular problem, we can represent the weight as the chromosome representation. So each value in the chromosome represent the corresponding weight. So if I take let's say I will take let's say 5. Okay, I'll say 0 0.5, 0 0.2, 0 0.3, 0 0.7 and 0 0.1. So these are representing the weight values in a particular chromosome. Now, if you go for fitness function, as I mentioned earlier also, we have one function called as objective function. We have another function that is called as fitness function, right? So sometimes we can take also objective function is same as our fitness function. Okay, I can take the same function as working as both genetic in a genetic algorithm or any problem. I can consider that function to calculate the fitness value. I can also use that function to minimize something, right? So GAR initially applicable for solving maximization problem. So minimization problems are transformed to maximization problem, which I already told you. Like if f of x is there, so for a maximization problem, I can write 1 minus f of 1 by f of x, and I can say that is a minimization problem. And if you see for some value of let's say x, you are getting the denominator is 0, so you add a minor quantity in the denominator. So like I have added a plus 1 in the denominator, so that value will not go, that f of x value, even if it is 0, so the denominator is not going to be 0, right? Now let us see one of the problem before going to the tag sibling problem. So there is a objective function that is given here. So the objective function says that pi of theta 1 comma theta 2. So that is my objective function. So you need two different input parameter. One is theta 1 and theta 2, right? In the range of theta 1, theta 2, which we call a source space, that is given in the range of 0 to 90. So once I give the value of theta 1 and theta 2, then you can solve this one. Right? For example, I'll give you theta 1 is equal to 0 and I'll give you theta 2 is equal to 90, for example. Okay. So you can write minus 4 sine 0, minus 6 cos 0, minus 4 sine 90, and minus 2 cos 90. So you will get a value, right or not? So in order to represent it a 4-bit string. Suppose I will take a 4-bit string. You can take more also, right? If you take 4-bit string means total degree is given to you is 90 degree, right? 0 to 90 is 90 degree. So if I divide 90 divided by 15, okay, because starting from 4 zeros to you will go up to 4 ones. Okay, so every 6 degree the code is going to be changed. Right, every 6 degree the code is changed. For example, if the fiber angle is 0, so I can consider 4 zeros. If fiber angle is 6, I am representing 0, 0, 0, 1. Like that, 90 will represent all ones. So you can see here. So successfully coded the input with the 4-bit string. Right. So somebody can say if the angle is equal to 5. So if angle is equal to 5, you have to choose the upper one, that is 401. Suppose angle is let's say 78. Okay, yeah, 78 is already there. So if the angle is let's say 82, so you will choose 31 followed by 0. So that is the binary encoding you have to use when you represent the chromosome. Now, if you go for the fitness function f, earlier I am saying a objective function. Objective function is nothing but that is f is equal to pi of theta 1 comma theta 2. So objective function may be same as fitness function or it may different also. So in this case, I took differently. So what is the fitness function? The fitness function says that f is equal to f dash minus 7, where f is our objective function. So when you calculate f dash is nothing but minus of f. So I can say minus of f minus 7. So as you know the f value, okay, which is minus, f value is pi of theta 1, theta 2. So I can write minus of pi of theta 1, comma theta 2 and minus 7. So this is your fitness function. Okay. So now encoding is done, right? Already we have done the encoding part, right? So if I generate some population, so you can take any population. Suppose I am considering, let's say 40 for theta 1 and 40 for theta 2. That means the angle of theta 1 is 0 and the angle of theta 2 is also 0. So we consider 4 zeros for the first angle and 4 zeros for the second angle, right? So which represent 0, 0. Theta 1 is equal to 0, theta 2 is equal to 0. That is a population. And similarly, suppose in initial population, as the first step in the genetic algorithm is initial population, so I consider the total number of population is 8. Okay, I consider total population is 8. So I represent in the form of what? I represent in the form of binary string by considering that each and every variable should be represented in 4-bit binary. So this is generated randomly. For example, if I say 0, 1, 1, 0, so you can go back to this table. 0, 1, 1, 0 means it represents the angle is 36 degree, right? The angle is 36 degrees. Similarly, 1010 represents the angle is 60. So with 36 degree, that means theta 1 is equal to 36, theta 2 is equal to 60. If you put in, let's say, capital F, which is minus f minus 7, which is equal to minus of pi of theta 1 comma theta 2 and minus 7. So you will get the fitness value, in which in the first case you have to put theta 1 is equal to 36 and theta 2 is equal to 60. So you will get the value as 4.66. So if you take a simple calculation, for example, I am calculating for population number 1. Okay, if I calculate for population number 1, then so capital F is equal to f dash minus 7, which is equal to minus f minus 7, which is equal to minus of pi of theta 1 comma theta 2 minus 7, right? So theta 1 value is here 0. So it is given you that theta 1 is equal to 0. It is also given that theta 2 value is equal to 0. So if you put in this formula, so you will get minus of, this is minus 4 sine theta 1. Okay, because pi of theta 1, theta 2 is minus 4 sine theta 1 minus 6 cos theta 1 minus 4 sine theta 2 minus 2 cos theta 2. So in which you have to put theta 1 is equal to 0, theta 2 is equal to 0. And we know sine 0 is 0 and cos 0 is equal to 1. As cos 0 is equal to 1, this will becomes 1. 6 into 1 is 6 you will get. But if it is 0, then you will, this term is going to be vanished, right? So if you calculate this one, you are going to get the fitness value is 1. Similarly, whatever population you have taken, right? Whatever population you have taken, so that populations, for every population, you have to calculate the fitness value. Suppose I said minimum value is better, then obviously out of these 8 population, 1 is minimum, so that is better. Suppose it is a maximization problem, then I can select 4.6 is the highest value, so that is better. Okay, so it is very important to note that objective function is the function that is going to be optimized, while the fitness function is what is used to guide the optimization. So fitness function is guiding the optimization, but objective function, what we want to achieve. That's why the function that are going to be minimized or maximized, that is called as our objective function. Now coming to the important part, I'll tell you the task scheduling problem. Let us see how you can apply this thing into the task scheduling problem in cloud computing. So here I am showing you two different computer, or you can consider in cloud term, these computers are virtual machines, or you can consider these two are simply the machines, or you consider these two are nothing but the data centers, right? You may consider different terms because you can see a number of papers consider in a different way. But I am showing you a simple example by using two different computers. And you want to carry out, let's say, four different tasks in these two computers. So you have four tasks and you have two computers, right? And these two computers configuration is different. Their configuration is not same. Okay, maybe computer one is powerful than computer two, or computer two is powerful than computer one. So for example, if you take this example, if you want to execute T1 on computer 1, then it is going to take 150 time units. You can consider second, millisecond, nanosecond, whatever may be. Okay. But if T1 is assigned to computer 2, it is going to take 18 unit of time. So for T1, you can say computer 2 is better than the computer 1. Similarly, if you go for T2, T2 case computer 2 is better than the computer 1, like T1. So it is taking 32 unit of time in computer 1 and 7 unit of time in computer 2. T3 case, it is taking 20 unit of time in computer 1 and 3 unit of time in computer 2. Similarly, T4 case, it is taking 50 unit of time in computer 1 and 15 unit of time in computer 2. So what I can conclude that irrespective of the task, computer 2 is better than the computer 1. So if you go for all possible number of scheduling solutions, that means T1 can be assigned to, let me represent by C1 as a computer 1 and C2 as computer 2. Okay. Similarly, T2 can be assigned to either C1 or C2. T3 can be assigned to C1 or C2. T4 can be assigned to C1 and C2. Okay. So these are possibilities. Okay, you can try anything you are going to choose, that is a giving you a solution. Solution may be better or not better, but you can try. So in this case, if you go for all possible solutions, then you will get total number of solutions is 2 to the power 4. For example, I can say T1, 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 T1 is a solution. Sorry, T1 is assigned to C1, T2 is assigned to C1, T3 is assigned to C1, and T4 is assigned to C1. That is a solution. That is one solution. T1 is assigned to C2, T2 is assigned to C2, T3 is assigned to C2, T4 is assigned to C2. That is also one solution. Somebody can say C1, C2, C1, C2 is a solution. C2, C1, C2, C1 is also a solution. Like that, how many solutions you will get? You will get 16. Okay, so we got 16 different solutions. So our source space is not bigger, right? In this case, the source space is not that much bigger. But when you go for L task and M computers, where L and M values are very large, the number of scheduling solutions you will get M to the power L. Like I mentioned, if I consider 512 number of tasks and 16 different computers, so it is 16 to the power 512, which is very large. But for easy illustration, what I am doing, I am taking only 16 different solutions. Now, if you solve this particular problem, let me show you what is encoding here, right? So I am taking a chromosome size of 4. Okay, there are 4 elements. In every chromosome, we have 4 elements. Where every element case, either you can put 1 or you can put 2. Okay, here you can put 1 or you can put 2. You can put 1 or you can put 2. You can put 1 or you can put 2. Right? For example, I am randomly generating it. So there is no other value you will get. Either you will get 1, which indicates that you are going to assign to computer 1. Okay, or you can assign it to computer 2. Okay, if it is 2, you have to think that you have to assign it to computer 2. So there is no other possibility. So one of the example I can say, one in chromosome 1, it is 1, 2, 1, 2. 1, 2, 1, 2. That indicates that T1 is going to be assigned to C1, okay, which will take 150 unit of time. T2 is assigned to C2, which is going to take 7 unit of time. T3 is assigned to C1, which is taking 20 unit of time. T4 is assigned to C2, which is taking 15 unit of time, right? So those types we are, I'm not writing T1 C2 time because T1 is not assigned to C2 as per this particular solution. So there is a concept here which is called as make span. Okay, make span means it is overall completion time. So overall completion time of C1, if you see, as C1 is assigned two different tasks, T1 and T3. So it will be busy for 150 unit of time for T1 and 20 unit of time for C2. Okay. So overall completion time you will get it is 170. But similarly, when you go for C2, you can see that C2 is executing T2 and T4. So overall completion time is 7 plus 15, that is 22. Okay, that is 22. So when you calculate the make span, it is nothing but maximum of 170 and 22. Maximum of 170 and 22 you will get is 170. So that is considered as the make span. Okay, so this is your fitness value kind of thing, you can say. But what is your objective? Your objective is to minimize this particular value. Okay, this solution you are getting 170. Another solution you may get the value below 100 also, right? If feasible. Okay, so obviously below 100 solution is better compared to 170. Okay, but that is a valid chromosome, right? 170 is also valid chromosome. That chromosome is also a valid chromosome. Like that, I took different type of chromosomes. So for easy representation, I am showing you here 10 different chromosomes. For example, if you go for chromosome 2, okay, chromosome 2, what is the solution? 2, 1, 1, 1. What it indicates? It indicates T1 is going to assign to the second machine. So that is 18. And T2 is assigned to the first machine, that is 32. T3 is assigned to the first machine, that is 20. T4 is assigned to the first machine, that is 50. Okay. So if you sum all the values, you will get 50 plus 20, 70 plus 32, you will get 102. So C1 is busy for 102 unit of time, where C2 is busy for 18 unit of time. So if you calculate the make span, okay, make span of the cloud, then you will get make span is 102. Okay, make span is 102. Similarly, I will show you another solution. I am taking chromosome 6. You know, in chromosome 1 case, we calculated and we got the value is 170. I am writing that value here. Chromosome 2 case, I am getting the value is 102. And in chromosome 6 case, it is saying 1212. So T1 is assigned to C1, which is taking 150 unit of time. T2 is assigned to uh, C2, which is taking 7 unit of time. T3 is assigned to C1, which is taking 20 unit of time. Okay, T4 is assigned to the second cloud, that is, it is taking 15 unit of time. So you can see the solution is same as the solution which we found in the previous case. Sorry, this is 22. Okay, so in the previous case we got a maximum of 170 and 22 we are getting, that is 170. So whatever result you got in the case of chromosome 1, the same result you are getting from chromosome 6. So as you are generating these chromosomes represented using random numbers, so there is also a possibility that there are some duplicate chromosomes. Like here you can see chromosome 2 is same as chromosome 1. That's why the result you are getting is same. Not necessarily you are going to get the unique solutions. Sometimes you may get a duplicate solution as well. So now I am showing you the make span of all the chromosomes. Okay, so by looking into this, as I said, our objective is to minimize the make span. Our objective is to minimize the make span. So what we can do? We have to select the minimum one. Out of these, we have to select the minimum one. So which one is minimum one? Chromosome 5 is minimum. So I can say out of 10 chromosomes, the chromosome number 5 is giving you a good solution. Similarly, I can say you chromosome number 3, if I'm correct, 3 and 8 is providing poor max span. The max span is not at all good, but they are providing solution. Solution may be good or bad, but they are at least providing solutions, right? So you can apply different type of selection methods that I'll tell you in subsequent slides. So you can apply tournament selection, you can go for rank selection, you can go for elitism. Okay, there are different type of selection methods are there. Using that methods, you can select it. Now, for example, I have a very simple selection method. My selection method says that you select the best 4 population. So best 4 population I am getting here, that is chromosome 5. Okay, is the best one. Second best is chromosome 4. Then next best is chromosome 10. And next best is my chromosome 2. So my selection process, I am not following any selection method that is given in genetic algorithm. I have my own selection method by saying that I am taking 10 population and I am selecting 4 best populations. So we found chromosome 4, 5, 4, 10 and 2 are the 4 best selection or 4 best chromosomes that are selected in the process of selection. So that we call as initial new population. So initial population, we have 10 chromosome, then followed by selection process, we selected only 40%. So we have 4 chromosome in our new population. Now what we will do? I told you up to this, the process is what? Up to this, the process is unidirectional. It is not going to be repeated. Initial population is done once, selection is done once, new population is also done once, right? So the chromosomes are 2, 4, 5, 10. So it is better to rename these chromosomes. So I rename it by 1, 2, 3, 4. For easy illustration, I have renamed it. Now what I have to do? I have to check what is the termination condition. Okay, termination condition, let us assume that the termination condition is that the number of iteration is equal to 1. Means after one round of genetic algorithm, you will stop. So number of iteration is equal to 1. But till now we have not done any iterations. So this condition is not satisfied. But when you come in the next iteration, this condition is satisfied. So you are going to end the loop, right? So here termination condition is not satisfied. So we have to go to the next process that is called as crossover. So as I said earlier, crossover is performed with parents. Okay. So I have selected 4 different chromosome here, right? 1, 2, 3, 4. Out of 1, 2, 3, 4, randomly I have to select 2 parents. So let us take a generation of the random number. If you generate the random number, here let's say you are getting 2 parents as 1 and 3. Okay, one chromosome is 1, another chromosome is 3. Okay, and let's say crossover point is 2. Okay, so I'm taking parent 1. You know, parent 1 chromosome is 2 followed by 3 ones, which I have written here. Then parent 3 is uh, 2 2 followed by 1 2. Okay, 2 2 followed by 1 2. So I kept 2 different parents. You can select any parents, right? But that is done through the randomly by following a random process. So what I got here, I got 2 1 1 1 and 2 2 1 2, and my crossover point is 2. 2 means after 2 values, right? So children 1 is generated as 2 1 followed by 1 2. So you can say 2 1 1 2 is my first children. Okay. Similarly, first part of parent 3 and second part of parent 1 is children number 3. So that is 2 2 1 1. Right? But we know what is the result of parent 1, and you can also see the evaluation of children 1 and children 2, but these evaluations are not done now. After the process of mutation only, we are going to check whether the children one is better than the parent one, or you can say modified children one is better than the children one, or modified children three is better than children three, or out of these four, which two are best. So you can see I have selected randomly. Okay, randomly we select a position for children one, because mutation case you have to select a particular position and you have to change that particular bit, right? And the process whichever we have followed in the crossover is called as 1-point crossover. Okay, in a particular point we have performed the crossover, 1-point crossover. So here what we will do, I'll select, let's say, a particular position and I'll change the value. For example, I have selected the second position randomly, and I have changed it to let's say another value, that is 2. Okay, the value is earlier 1, but now I have changed to 2. Similarly, I have selected another position in the children 3. Okay, let it be the position number 3, and I have changed that bit to 2. So I have done 2 mutation. Mutation means you have to select one particular point and change that point. We have only 2 possibility, right? 1 and 2. So either 1 is going to be changed to 2 or 2 is going to be changed to 1. Okay, sometimes also as we are using random generation, 1 may be replaced with 1 and 2 may be replaced with 2 also. So now you got modified children 1 and modified children 3. So always remember, comparison is done between parent 1, parent with modified children. So you have to compare modified parent with modified children. For example, in this case, we have taken 2 parent. So parent is giving 102 and 40. Okay, parent 1 is giving 102, parent 3 is giving 40. Similarly, modified children case, you are getting 40 and 50. 40 and 50. So if you compare parent 1 with modified children 1, obviously modified children 1 is better. But when you compare parent 3 with modified children 3, so parent 3 is better. Or if you take overally, also you can see these 2 chromosomes are providing you better make span compared to other solutions, right? So you can keep parent 3 as it is, and you can replace the parent 1 by modified children 1. Okay, so here you can see I have replaced parent 1 with modified children 1. So here I am showing you as 1 crossover and 1 mutation. But when you go for genetic algorithm, we are doing a couple of crossover and a couple of mutation, not only one. You can do crossover and mutation several times, not only a single time, several times. So if you do this one, then you can see all the values after a couple of iteration, as our objective is minimize. So after a couple of iteration, you will get all the values will converge to, or will comes to a particular point where the optimal solution lies. Yeah, if anybody is having any question, you can ask.
Good evening, sir.
Yeah, sir, please.
Can you hear me?
Yeah. Please continue.
Sir, my question is, what is the criteria to perform mutation in the given child, I mean, or parent?
There is no criteria, but
Mhm.
there is a mutation rate. Okay, how many mutation you can do? There is a limitation in that. There is a bound for that. But you have to select it randomly. Like you can see, in this case, I have generated a random number in between 1 to 4. Let's say my random number is coming 2. So I am selecting this particular position. Then in this position, the possibility is that either you can go for 1 or you can go for 2. So I am again generating a random number in between 1 to 2. Let's say I am getting the random number is 2. So I am replacing this particular 1 by 2. Okay, there is no specific criteria.
Okay.
Okay.
Yeah.
Yeah, but I'll tell you in subsequent slide how many mutations you can do and how many crossovers you can do. That I'll tell you.
Okay. Thank you, sir.
Yeah. So this is one round. Okay. After doing a couple of round of crossover and mutation, you will update the population. So this process we are repeating. You can see this is a one dimensional process, right? but this process we are repeating. Okay, this is we are repeating until unless our termination condition is satisfied. Once our termination condition is satisfied, we are out of this particular loop, and we'll see in our new populations, whatever populations are there, which population is giving you the best value, and that value is going to be returned to you. So although in cloud case, many people have solved this particular problem. Yeah. So here I think I am doing another round, right? Yes, I am doing another round. So you can see after one iteration, our objective is fulfilled, right? You can see here we have selected modified children 1 because modified children 1 is better than parent 1. And I am keeping parent 3 as it is because modified children 3 is not giving good value. So this is my new population. I have updated my chromosome 1 with modified children 1. So you can see in the first round, if you see, let me go back. Yeah, these are the populations you have taken, right? So the worst max span you got is 102 and the best you got is 40. Okay, 40 to 102. But after one round, what you are getting here, you can see you are getting highest is previously you are getting 40 to 102, but now you are getting in the range of 40 to 70. So although you have not improved after one iteration, you have not improved the best value, but you have improved the worst value. Okay. So now I am checking whether the termination condition is satisfied or not. So as I said earlier, I am taking the number of iteration is equal to 1. So termination condition is now satisfied. So what I have to do, I have to stop here. Once I stop here, I'll check which make span is better, right? Out of these population, which population is better? Chromosome 1 and chromosome 3 is providing you the same result. So I conclude that the solution that is going to be written is 40. But normally we took around 20, 30 iterations. Sometimes we go 50 and 100 iterations also before making such conclusions, right? So this way you can apply, you can say, genetic algorithm into the task scheduling problem, right? But what are the selection methods? What are the crossover mutation is there? That I'll tell you in the subsequent slide. Because here I have used a very simple method. You calculate the fitness value, and based upon the fitness value, you select the 40% of the population, right? So you can extend this particular problem like in the previous problem, I considered that a task can be assigned to any computer or any virtual machine or any data center or any cloud, but it is not true. So sometimes a task can be assigned to only limited number of systems. It is not possible to go for each and every number of systems, right? For example, you can see T1 can be assigned to computer 1, computer 2, computer 4, but the requirement is not satisfied in computer 3, right? Similarly, T7 can be assigned to computer 2, 3, 4, but not to the computer 1. So this we generally refer in cloud as a quality of service. So QoS is not guaranteed in this machine, so it is not capable to handle that particular task requirement, right? So in this case also you can apply genetic algorithm and find the solutions. Okay, so coming to the selection operators. So there are number of selection operators we have. And selection is the very first operator that we are applying to the population. So the main purpose of selection is many cases there are three different types of population you will get: above average, average, and below average. So generally, below average populations we are discarding, and above average populations we are creating multiple copies, and average populations we are keeping as it is. So I'll tell you some of these methods so that you can understand how the selection process is done. Although I told you a very simple solution by taking only 4 population, there is 40%, but there are number of selection methods are there. So we'll start with the roulette hill, then we'll discuss about Boltzmann selection, tournament selection, rank selection, and steady state selection methods. Okay, coming to roulette hill. In roulette hill selection, suppose I am taking 8 different population, which I told you earlier. Every population is represented as 8 bit. 4 bit is representing one angle, another 4 bit is representing another angle. And we know how to calculate the fitness value. Fitness value is minus f minus 7, where f is equal to pi of theta 1 comma theta 2, and the expression is there that you have to solve. Suppose you are getting these are the fitness value. So in relative selection, what you will do, you will calculate the sum of all fitness value. So every population has a fitness value. We have 8 population. So I can find sum of all fitness value. If you calculate sum of all fitness value, you will get the value is 23.27. 23.27. Okay. So I am calculating now probability of a ith chromosome. What is the probability of selecting population number 1? What is the probability of selecting population number 8? So how to calculate? What I'll do? 1 divided by 1 means the fitness, current fitness divided by sum of all fitness. So if I do it, I'll get 0.0429. Similarly, for population number 2, probability is 0.09 divided by sum of all fitness is 23.27. So you will get 0.09. So like that you have to calculate. So if you calculate the PI, okay, of each and every population, obviously we are calculating the probability. Probability, if you sum it, you will get the value as 1. Okay. So as the name suggests, it is a roulette hill. So there is a wheel. In that wheel, you have to give, you can say, you can divide this wheel into number of sections based upon this probability. For example, if it is 0.0429, so let it be 5%. Similarly, this is 9%. This can be considered as 13%. Next is 17%, 20%, like that. So this much area will be covered by that particular population. So let us see here. So you can see a wheel. Now we have 8 populations starting from population 1 and population 8, and they have occupied based upon the probability. And probability is calculated based upon the corresponding population fitness divided by sum of fitness. Okay. So if you look into this wheel, you can see 8th population and 5th population occupied 20%. Okay. So when we spin this particular wheel, or you rotate this particular wheel, so there is a high chance that either a population 8 is going to come or population 5 is going to come. Right? If more area is covered, high chance is there. Like if you go for a lottery, okay, in the lottery, let's say 100 cheats are there. Out of 100 cheats, let's say 2 people is having 60 cheats. Okay. So the probability of selection is quite more in comparison to others, right? But you can see cumulative probability we have calculated. So actually the selection is based upon a particular method. So for that, after finding the probability, you have to calculate cumulative probability. So you know cumulative probability is nothing but sum of all the probability, right? For example, we have seen this PI. Now if you come to the column A is called as expected count. So expected count is calculated based upon the probability multiplied by number of populations. So number of population we have taken here is 8. So 8 multiplied by probability. Okay, for example, in this case 0.0429 multiplied by 8, you will get the value is 0.33. Right? Now, if you go for cumulative probability is represented in column B. Like for first one, the cumulative probability is as it is. But when you go for the second one, you have to add these two. That is 0.0429 plus 0.0900. If you add it, you will get 0.1329. That is written here. So column B represents the cumulative probability. Next, what you have to do? C column represents a random number. You have to generate in the range of 0 to 1. Okay, any value can come if you generate in the between 0 and 1. Now you have to check that. Suppose I am taking the random number is 0.259. So I have to find a particular population whose cumulative probability is greater than this particular value. So obviously, when I check with 0.04, 0.04 is very less. 0.13 it is less, but 0.266 it is more compared to 0.259. So that particular population I have writing here. So in this case, a 0.266 is greater than 0.259. So I am taking population 3. Okay, population number 3 I am writing here. Similarly, if it is 0.038, 0.038 case, 0.0429 is greater than 0.038. So I am writing population number 1. Okay, in that way you are filling the column number D. And column E is based upon that how many times 1 is repeated in column D. If you look into column D, how many times 1 is repeated? Only one time. How many times 3 is repeated? One time. How many times 2 is repeated? One time. How many times 4 is repeated? 1, 2. That's why this value is 2. So those strings or those populations, okay, those population is above average populations. So that you have to duplicate. For example, in this case, as you are getting 2, it is duplicated twice. As it is 5 is also 2, it is duplicated twice. And these two chromosomes, if you look, population number 6 and population number 7, it is 0. What it indicates? It is below average populations. That's why the population number 6 and 7 is discarded. Okay, so if in E column the count is 0, then you have to discard it. If count is 1, you have to keep as it is. If the count is 2, you have to duplicate it. Okay, in this way, so I am taking 8 different populations. Okay, in initial population, I apply the process of selection, and I am getting the number of new solutions is also 8, right? Although we discard two different chromosome, as we have duplicated, it is compensated. So initial population case also it is 8, new population case also it is 8, right? But there are some issues related to relative selection. So that we call as population diversity. Another is called as selective pressure. Okay. So what is that in overall sense? I can say suppose some populations is dominating other populations, so the probability of getting the population that is having low probability is very less. So in order to avoid this one, other selection methods are there. So population diversity means the genes that are already discovered as good individuals. Like in the previous case, we found the good individual is 4 and 5. So they are going to be exploited, while promising the new area of source space continue to be explored. You are not only exploring good individual, in population diversity says that you are exploring that only, but you should also keep in your mind that other populations are also there that also need to be explored. Because in the next generation cycle, it may happen that others may perform better than this, right? But when you go for selective pressure, is the degree to which the better individuals are favored. That is also not good here. Because if they are having higher probability, they are getting more space. So probability of getting is more. Okay. So these two impact the performance. So convergence rate of genetic algorithm is largely determined by these two, population diversity and selective pressure. So if there is a high selective pressure, then convergence rate is also higher. Alternatively, I can say low selective pressures, then there is a slower convergence rate. So you have to balance it. Okay, you should not always favor the good individuals, but also you need to explore the other individuals also, because we don't know who is going to perform in the next generation cycle. Another population may be the better in comparison to the previous one, right? And if you put excessive selective pressures, in selective pressure is very high, then GA is prematurely converging to a local optimum solution. And it is not possible to reach to the global optimum solution. This is because also the population diversity of the source space to be exploited is lost. Right? That's why these two are the issues which is overcome by other selection methods. Now, for example, if you go for tournament selection. So tournament selection is same as playing a match between two different teams, right? Like we have cricket matches, we have football matches, we have hockey matches, right? So two different teams are playing, and one team is going to win, another team is going to lose. So tournament selection provides selective pressure by holding a tournament competition between two individuals. And the individual who is having higher fitness value, because it is a maximization problem, so that is better. For example, past tournament we are playing with individual 2 and 4 or population 2 and 4. And the fitness for population 2 is 2.10. Fitness of population 4 is 4.01. So who is better? If it is a maximization problem, 4.01 is better. So 4 is selected, 2 is ignored, right? Similarly, uh, if you go for another match, okay, in another match I am selecting two individual, that is uh, that is team number 3 and team number 8. In team number 3, the fitness value is 3.11. Team number 8, the fitness value is 4.55. Okay, so we know that population number 8 is better than the population number 3. So I am selecting 8 as the 8 is considered as the best. 8 is the winner. 8 is the winner of the match, and 3 is the loser of the match, or it's because 8 is having good fitness, right? Similarly, you have to play a set of matches, right? Suppose I am playing 8 matches, and I found that like I conducted between 2 and 4, 4 and 5, 1 and 6, 1 and 2, 4 and 2, and 8 and 3. So one team is going to win, another team is going to lose. So after 8 matches, I found that population 2, 3, 5, and 6, they are selected only once. And population 4 and 8 are selected twice. And population 1 and 7 is not won a single match. So what we will do? Population 1 will discard, population 7 will discard. Okay. And in place of population number 1 and 7, we will duplicate 4 and 8. Okay. So it is above average, this is average, and this is below average. So below average populations we have to discard. Above average populations we have to duplicate, and average populations we will keep as it is. So if you compare the ruler till selection, in which we have omitted 6 and 7, but tournament selection case we have omitted 1 and 7. But still the problem is not solved, right? If you see the area wise, if you see in the tournament, our ruler till selection, so the population which is having higher probability will occupy more space. So in order to avoid that, we are going for rank selection. So in rank selection method, what happened? Like this is the problem with the ruler till. So as let's say population 5 is occupied 75% of the area. So when you spin that particular wheel, you will get a chance that the population 5 is only going to come. So in order to avoid that, we are going for rank selection. What rank selection is doing, the population which is having more probability is given the highest rank. Highest rank means if it is 5, so I am giving the rank as 5 to fifth individual. Then out of these 4, this is considered as 4. This is considered as 3. This is considered as 2. And this is considered as 1. Means the population which holds the population which covers very less area is given as the rank 1. Rank here highest rank means the higher value is considered as highest rank, right? Not 1 is the best rank, right? So similarly, these are the ranks we have given it, and sum of the ranks we are getting is 15, and we are calculating the percentage. Percentage is your rank divided by sum of the rank. So we are getting 7% for population 1, 13 is for population 2, 20 is for population 3, 27 is for population 4, and 33 for population 5. So you will get this particular wheel. So you see, if you compare these two wheel, more or less this wheel is a you can say paired one in comparison to the previous one. Okay, so rank selection ranks the population and taken every chromosome receive fitness from the ranking. It is based upon the ranking. It is not based upon the probability. Okay, so that every individual will get some space in the wheel. So there is a likely chance that more people will get. Because you can see 75 is reduced to 33, which is obviously a good solution, right? There is another method that is called as elimination, right? So here it also says that based and few based chromosomes are copied to new population. So Goldberg and Samtani, they did the first application in genetic algorithm, right? So they suggest that fitness of any ith individual must be subtracted from a large constant. Okay, but you have to make ensure that fitness values are non-negative. Then only you have to make it a constant. Otherwise, negative will be positive, and it will be a large value. So for minimization problem, the new expression for fitness is you have to calculate fmax minus fmin minus of fi of x. And if fi is positive for maximization problem, then we consider phi I is equal to fi. So let us take an example. So we know the average fitness is 2.908. If I take 8 population and calculate the fitness, and if I calculate average fitness, it is 2.908. And if you calculate f divided by f bar, f is the fitness divided by average fitness, I am going to get these values. And by looking into these values, you can see the lowest value is 0.30380. That means population 1 is below average. 0.738 means 6 is also below average. And if you go for higher value, because it is a maximization problem, 1.802, 1.760 is above average. So we have to duplicate these two chromosomes and we have to discard the population number 6 and population number 1. Okay, so the worst fit individual die off. Here the worst fit individual means population number 1 and population number 6, they are die off. And a mating pool is created where individual 1 and 6 are die off. And in place of 1 and 6, we are placing what? Population number 5 and population number 7. And there is a concept in genetic algorithm that is called a generation gap. Like if you remember what we discussed in task scheduling, we took 4 population. Out of 4 population, you can see 1 population is replaced in a cycle. So generation gap is calculated based upon number of population and how many populations are going to be replaced. So in our case, if you see, our population size is 4. Okay, our population size is 4, but we have replaced only 1 population. So our generation gap is 0.25, right? And there are several other schemes are there, like selection of the parents can be done based upon the fitness. Selection of replacement can be done randomly. Or first one is random, second one is based upon the fitness or inverse fitness. Or both can be done when based upon the fitness wise and inverse fitness wise. In this way, you can make the selection process. Now, the next process that is called as crossover. So I told you in task scheduling problem, we consider the crossover as a 1-point crossover. We selected the second point and we perform the crossover. But crossover can be done in different way. Like task scheduling problem, what we did, we have selected a crossover point. This is, let's say, our crossover point. A is a parent and B is a parent. So I am taking the first part of parent 1 and second part of parent 2. Similarly, I am taking the first part of parent 2 and second part of parent 1. So I am getting A star and B star, which are 2 children. Okay. So in order to perform crossover, you have to decide which 2 chromosome you will select. First, you need 2 individual strings selected. You have to select based upon new population. From the new population, you have to select, and you have to also select one cross-site point. In which point you want to do crossover. Okay, and after that, you have to perform the crossover, right? So if you go for single site crossover, then you have to select a particular point. Like here, I am selecting the point is another example. I am selecting the point is 5. So I am taking first part of parent 1, second part of parent 2. Similarly, first part of parent 2 and second part of parent 1. That will be child 1 and child 2. But some case I can take 2-point crossover. In 2-point crossover, I'll take cross site point 1 and cross site point 2. I'll take first part of parent 1, second part of parent 2, and third part of parent 1. Similarly, I can take first part of parent 2, second part of parent 1, third part of parent 2. Okay, so I can generate the children like this. Some people have already also applied a multi-point crossover. So you can see multi-point crossover is itself of two types. You can go for even number of cross sites or odd number of cross sites. For example, if I consider a ring has no start point and end point. So let's say I'm selecting one particular point. Okay, here. And these are the different points. Okay. So I am taking 2 points, two rings. One is for parent one, another is parent two. So I'll take one part of parent one and one part of parent two, another part from parent one, another part of parent two. That will be child one. Similarly, the alternate case you will get child two. But if there is a starting point or ending point, just like a line, if I take, so I can take different number of cross sites. For example, this is my parent one, which is a straight line. Parent two is a bold line. So I am taking uh, this simple line followed by a bold line, followed by a simple line, followed by a bold line. That can be considered as a crossover, right? So you have to decide that which crossover is suitable for your approach. Like many people also works in a particular problem in which metrics come into picture, especially image processing applications. Okay. So on that case also you can apply crossover, right? For example, if I consider this is parent one and parent two, then I'll take one part from parent one, another part from parent two, or one element from parent one matrix element from parent one, another matrix element from parent two, and like that you will proceed throughout the matrix. Okay, so many research also suggested, including Dept in 1995, so they mentioned that it is difficult to generalize the optimal crossover operator selection. Like if you ask for a particular problem or task scheduling problem, whether you go for 1 point crossover, 2 point or multi-point, so there is no answer. So you have to try all possibility and you have to check that which crossover works for you. So the next important part is crossover rate. So what is the crossover rate? Crossover rate says that it is a ratio between the number of pairs to be crossed divided by fixed population. So for example, if the population size is 30 to 200, we have taken only 10. Okay. But normally we take population size is 30 or 50 or something like that. So if the population size is 30 to 200, the crossover rate is 0.5 to 1. That means the number of crossover, suppose you are taking 30 is the population. So number of crossover you can do is 15 to 30. Number of crossover per cycle that you can do is 15 plus 30. Okay. So minimum number of crossover you have to do is 15. If the population lies in this particular range, and normally we take the population in this particular range only. Okay, for example, if I see a crossover probability of PC is used and only 100 PC percentage strings in the population are used in the crossover operation, then 1 minus PC percentage of population remains as it is. So 50% population if you are changing, rest 50 population will be as it is, which I told you in generation gap. How many populations you are replacing and what is the total number of population. But the problem with this crossover is that even if you are doing any point of crossover in a particular point, if all values are 0, it is not possible to make it 1. Okay. If one particular bit, all values are 0 or 1, it is not possible to go for another bit. So in order to perform this one, what we are doing, we are going for the process of mutation. Okay. So what we will do in mutation, we'll select a particular element. For example, I am selecting this particular element and I am changing it. Okay. So I'm selecting this particular element which is 0 and I have changed this bit to 1. Similarly, if my population consists of real number, I am selecting a real number randomly and I am replacing with another real number. So if your population size is in between 30 to 200, mutation rate you have to take is 0.001 to 0.5. Okay, mutation rate is 0.001 to 5. Means if you are taking 30 populations, maximum number of mutation you can do is 15, not more than that. Because too much mutation is not good, right? Because population is going to be changed. So we don't know whether we'll get a good solution or not, right? Okay, so this is the complete cycle. So in this problem, I am considering the number of ones as fitness. Okay, how many ones are there out of 10 is called as my fitness. For example, if I take this particular population, 3 out of 10 Okay, 3 number of ones are there out of 10 bits, so its fitness is 0.3. Similarly, if I consider the last one, the number of ones is 9 out of 10, so fitness is 0.9. So if you calculate f divided by f average you will get 0.6. So fitness divided by average 1, 0.3 divided by 0.6, I am getting 0.5. Because once you calculate the fitness, okay, comparison by taking the average fitness, then only will come to know that which fitness is better, which fitness is not better. So in this case, you can see if again the highest value is better, then this population case we are getting poor value. So we are going to discard this particular population, and we have to select population number. Is highest fitness is population number 4. We have to duplicate that particular population, and rest we will keep only one time. So this is always this is also called as Darwinian theory of survival. We say that above average need to be duplicated, and below average need to be discarded, and average individuals you have to keep only one copy. Okay, so now if we want to perform the crossover, suppose I want to do crossover between 1 and 4, and the cross side points are 1 and 5. Okay, cross side point is 1 and 5. So after, suppose if you are taking this one, you can do cross side point 1 is this one and cross side 5 is this one. So you can generate new population. So if you are taking 1 and 4, so I can say 1 will be 0, 4, 1. Okay, then 11100 is one population, right? Similarly, the alternate one can be considered as another population. Okay. Again, you can apply the process of mutation. So if you go for the process of mutation, okay, anyhow, you are doing pairing here, mutation crossover here. 1, 1, 4 you are doing crossover. 2, 3 also you are doing crossover. Okay. So let's say pair 2, 3 is left intact, but population number 1, 4 is again changed. Okay. So after performing crossover, what you can do? You can do mutation. Suppose mutation we are applying to 6th bit of string 2 and 1st bit of string 1. Okay, that we can do, right? 6th bit of string 2 and 1st bit of string 1, right? So 2 out of 40 bits are muted. So the mutation probability is 0.05, because I told you maximum we can go for 15. Okay, if the population is 30, right? Maximum is 50%. So if the 30 population means we can go for 15. So like that, you have to apply the process of mutation, crossover followed by the mutation, and you have to do couple of rounds in order to satisfy your termination condition. And once your termination condition is satisfied, then you have to stop and you have to find which population is giving you the best value, and that value becomes your near optimal value in genetic algorithm. Okay, so this is the complete cycle which I told you in genetic algorithm, which you can apply in your respective domain. And in cloud also we have several cloud case. We have several different type of problems. Not only this task scheduling problem, other problems are also there. So which you can apply the genetic algorithm to find the solution. And you can see in the field of wireless sensor network also there is people have applied a genetic algorithm and particle swarm optimization. Okay, this is about PSO, and this paper talks about genetic algorithm. This is GA, and these papers are talking about PSO, which you can refer if you want to know more about genetic algorithm and particle swarm optimization. Yeah, thank you everyone. If you have any question, you can ask.